Let's talk about the respiration rate. The respiration rate is the amount of breaths or respiratory cycles per minute, and it's actually regulated by the medulla oblongata. One of the functions of the medulla oblongata is the regulation of cardiovascular and respiratory functions. This image right here is the peripheral chemoreceptor system. So the medulla is responsible for generating breathing movements and regulating respiration to ensure that there's enough oxygen in the blood. This is done by using chemoreceptors detecting changes in oxygen and, at a lesser extent, changes to carbon dioxide. Most of the chemoreceptors are in the carotid bodies, which are right here, but we also have chemoreceptors in the aortic bodies, which is in the aortic arch. The carotid and aortic bodies are the primary chemoreceptor organs measuring pH, partial pressure of CO2, and partial pressure of oxygen. Carotid bodies are particularly more sensitive to partial pressure of oxygen than aortic bodies, which are more sensitive to pH level changes. So each chemoreceptor body receives its own blood supply through a small artery from the adjacent arterial trunk. This means the chemoreceptors are exposed at all times to arterial blood, so their partial pressure of oxygen values are arterial partial pressure of oxygen values. When the oxygen concentration falls below normal, those chemoreceptors are going to become stimulated, which is what you're seeing in this image right here. The different levels of partial pressure of oxygen is affecting the rate of impulse transmission from a carotid body, especially when we're in the 60 to 30 millimeters mercury zone. This is where hemoglobin saturation with oxygen decreases rapidly. So we're going to see a really high increase in the impulse per second of the carotid body nerve. And that nerve is going to send a message, a neurotransmitter, to the medulla oblongata, letting them know we need to increase the respiration rate. So as talked about in BME 280, we can't increase the speed or the magnitude at which action potentials are fired. We can only increase the frequency. So the medulla is going to increase the frequency at which nerve impulses are being sent to the diaphragm and the intercostal muscles so that they can relax and contract faster, which is going to increase the rate of breathing, as we see here. I also wanted to briefly mention how abnormalities in the respiration rate can be displayed not only in ECG signals, which we already knew, but also in EEG signals. We know that ECG measures heart rate and heart rhythm. So during inspiration, the lungs stretch the heart towards the abdomen, and in expiration, the emptying of the lungs is going to compress the heart towards the chest, towards the breast. Due to the placement of the heart, the electric cardiac vector is going to change during respiration, which is going to be displayed as an amplitude modulation on an ECG. And this image right here is going to show, although this is a little bit newer, we see changes in respiration rate that can be seen on an EEG as well. For example, slowing down your breathing rate during meditation or controlled breathing. EEG measures brain waves, which we know, and classifies them based on frequency. Controlling breathing can cause physiological effects caused by the parasympathetic system. Caused by the parasympathetic activation, such as decreased oxygen consumption, decreased heart rate and blood pressure, and also an increase in the production of alpha waves in the brain, which is measurable with EEG.